Hi there. This video is reviewing the two main ideas in section 3.7 in preparation for to do section 3.9, which is the video that follows this. 3.7 had us do word problems, applications, using the advanced version of the chain rule, and it restricted itself to two variables. 3.9 basically does the same thing, but with more complicated word problems and more than two variables. If you feel comfortable with setting up word problems and with the chain rule involving multiple variables, more than two variables, you can skip right ahead to the 3.9 video, or you can follow along if you want to do some quick review. All right, so let's dive into it. I'm going to start off with a couple of just a simple two variable word problems. Then we'll go to more advanced chain rule, and then I'll give a simplified version of the a three variable version of the advanced chain rule word problem. Okay, so we're going to start off with this example A right over here that says the height of a tree in feet can be modeled using this formula. F of t is equal to 10 times e to the 0.5t. You may recognize that as an instantaneous exponential growth model or a continuous growth model. T in this case is measured in months after the tree has reached 10 feet. And we're looking for how fast the tree is growing after 1 year. Okay, so this is a word problem. It involves a couple of variables, the output variable f and the input variable t, and it involves a tree. Now, you can draw a tree if you'd like. For a lot of these word problems, a visual medium is oftentimes very helpful in trying to organize your information. Depending on your artistry level, it may or may not look like my tree. In this problem, I don't think it's quite necessary to draw a tree unless you really want to. They do give us a function. I'm going to write this as a y because I'm not a big fan of the more complicated function notation. So I'm just going to write this as a y equals, just to make it easier for me to write down the calculus stuff. It is very important to write down what the variables represent. As the problems get more complicated, this will be a habit that you will really appreciate. So t, according to the problem, is number of months, and it's number of months after the tree has reached 10 feet. Whoops, 10 feet tree. And we have the y variable, which according to this, the height of the tree in feet. Okay, so writing down sort of the information and keeping it organized is a key component to doing word problems. So kind of keep that in mind, read the problem carefully, identify the important information, read over the question, make sure the question is related to the information that you've identified as important. So we're doing all that prep work right now. So this information that we have here is the function. We have how the variables are defined, and we also need the question. So the question is, how fast is the tree growing after 1 year? Now, it's important now to use the variables to write down the question in a format that's mathematical and not just a sentence. So how fast is the tree growing? Well, something grows means they get taller, right? The feet change. And this is changing in time, right, after a year. So we're looking for, we want, so I'll write it over here, we want the change in the feet over the change in time. That would be the how fast, the rate of how the tree is growing in time. And we're looking for that after 1 year. So this is after 1 year. Now, 1 year, by the way, we could write down 1 year, but again, I really recommend that you utilize the variables. It's going to make your life so much easier than sort of getting to some point and wondering what to do next. What are our variables in this problem? Well, our variables, oops, make this go away, sorry. Our variables, let's go back to this thing, are y and t. T is the time variable, and t is measured in months. Why is it measured in months? Because we were told in the problem it was measured in months. So the evaluation of this derivative is not at 1 year, it's at 12 months, which is equivalent to 1 year, but it's got to be 12 because it's measured in months. All right, so we know what we have, we know what we want. Let's go ahead and find it. If we're looking for dy dt, the only way we're going to find dy dt is to find some sort of formula, some sort of equation that has y in it. It's the one we were given. And then we differentiate with respect to t so we can find dy dt. So I take my formula here, I do the derivative with respect to t on both sides, and that's how I find dy dt. So the derivative of y is just 1 times dy dt. And the derivative of this thing, the 10, because it's multiplied, doesn't affect the derivative. The derivative of e to a function, e to a thing, is e to the thing times the derivative of that thing. That's our chain rule. And so we get dy dt is equal to 10 e to the 0.05t, and then the derivative of 0.05t is 0.05 dt dt, which is just 1. So we don't need to write this because it multiplies and goes away. Finally, we're looking for not dy dt in general, but dy dt specifically when t equals 12. So then I can write dy dt when t equals 12. Well, that's just going to be plugging in 12 into our formula. Times 0.05. And I did this on Desmos over here. This line right here, 0.5 times e to the 0.05 times the 12 months, and I get about 0.911. So this is going to be about 0.911. And the units of this, remember the top part is the change in y. Y is measured in feet. So this is going to be how many feet change, or the change in feet. The bottom is dt. T is measured in months. So that's going to be the change in months. So the rate is 0.911, approximately 0.911 feet per month. So at this instant, at this moment that the tree is 12 months old, 1 year old, at that moment in time, it is growing, it is increasing in height at the rate of 0.911 feet per month. All right, so there's the idea of a word problem using calculus, using rates, using the chain rule. All right, let's do a little bit more complicated one. Then we'll do some practice on lots of more variables, chain rule, and we'll be kind of finishing up our little review video after that. All right, so the next example we have here is a cylindrical pipeline. It has a fixed radius of 10 feet, and its length is increasing. So depending on your sort of visualization and your geometry, this one you might want to draw a picture of. I do have a cylinder. Let me change that color. I have a cylinder. I don't know how to draw a cylinder, but it's kind of like a couple circles with connected like that. So that's kind of like a cylinder. You get the idea. It has a fixed radius of 10 feet. So this thing right here is 10 feet, the radius from here to here. And its length is increasing. So here's the length. And the length GTH, is not a constant. It's not like the fixed radius, right? So the length is changing. So I usually put little arrows to remind myself that that length is actually, moving around, right? In this case, it's getting bigger and bigger. There's some questions here. The first question, it says, how fast is the volume of the pipeline increasing with respect to its length? So we are looking for, why did I have length Y over here? I'm not sure what I'm doing here. LENGTH. Okay. Oh, that was my arrow. I can't even read my own handwriting. That's what's going on. Sorry. All right. So back to part A. We're looking for how fast the volume is changing with respect to length. So we need variables for volume and for length so we can actually write down the equations, right? So we need to math up this problem a little bit. So I'm going to be a little bit boring. I'm going to choose V for my variable for volume. And I will choose L for my variable for length. GTH. Now, according to this picture, that makes this distance from here to here the L. All right, that's my length. And then the stuff inside, which, I guess I can't really draw very well, but all the stuff inside is the volume. All right, so I have my picture, I have my information organized, I have my variables written down, and from here, we're supposed to find how fast the volume of the pipeline is increasing with respect to its length. So first of all, let's write down what we're looking for. We're looking for how fast the volume is increasing. That is the change in volume. And then with respect to, in other words, as its length changes, what length is L, so that's dVdL. So we're looking for dVdL, and it doesn't say at any particular time, it just asks for dVdL in general. All right, in order to find a derivative like dVdL, we're going to have some equation with V in it. Hopefully it has an L in it too, but it's actually not even necessary. It just has to have a V in it so we can differentiate with respect to L. So at this point, you're going to either have to look up the volume of this object or refer back to your geometry notes or send me an email and say, hey, what's the volume of a cylindrical pipeline? Somehow you have to get a formula, an equation for V, for volume. So this is a cylinder. You can look up if you want, but the volume of a cylinder is the size of the base, which is pi r squared, times the length or the height. So we're going to do pi r squared times L. Now remember, R is a fixed value. It says a fixed radius of 10 feet. So make sure that you write down the information. I put it in the diagram. You might want to circle as well, because if you don't, there's a good chance you'll be differentiating R, and that will be kind of messy, and it's actually not even going to be correct. So what is R? R is 10. So V is equal to pi times 10 squared times L. Or in other words, V is just 100 pi times L. All right, so that's our formula for volume. If we're looking for dVdL, then all I have to do is differentiate this thing, both sides, with respect to L, and that will give me dVdL. So dVdL, the constants being multiplied don't affect the derivative. The derivative L is dL dt, or 1 times dL dt. And that is the formula for how fast the volume of the pipeline is increasing with respect to its length. It isn't a numerical answer because the change in volume isn't always the same. It depends, right? I wrote down the wrong letters here. I'm differentiating respect to L, and I have the habit of writing dt down here, but that's not a dt. You may have noticed my mistake, and I did too. So we're differentiating respect to L, so it's dv dl. I think I said it correctly, and then I just wrote it incorrectly. This is the derivative is dl dl. Oh, so that actually means that I wrote it incorrectly too, because dl dl is equal to 1. So this actually goes away. So in this case, dVdL does not depend on time. It actually is always equal to 100 pi, no matter where we are. All right, that's very interesting. So the change in volume with respect to L, just my habit is just horrible, isn't it? The change in volume with respect to L is always 100 pi. And the units for that, the top unit is volume. Volume in this case is measured in, well, we didn't say what measured in, but volume is measured in, length is measured in feet. So volume is measured in cubic feet. Okay, so this units here for dVdL would be cubic feet. That's the change in volume. And then the change in length is feet. So this is cubic feet per feet. Please don't simplify this somehow to be feet squared. That's not the correct units. It's the increase of 100 pi cubic feet every increase of 1 foot in the length. So at that instant, or actually any instant, because it doesn't depend on any other variable. So always the volume is changing at that rate. Okay, so let's finish off these last couple of problems. In part B, here's the time one. So I was kind of doing part B ahead of time, I think. Part B asks, can we find how fast the volume of the pipeline is increasing with respect to time? Okay, so somehow I was like doing part of B in A. So in this case, I'm looking for how fast the volume is changing with respect to time. So that's dV dt. And I kind of did that already and I erased it. So let me just write it again. I got my volume formula. The radius is still fixed. So it's still going to be like pi times 10 squared times L, right? Or just 100 pi times L. And now when we differentiate this thing, 100 pi times L, when we differentiate this thing, we're going to be differentiating with respect to T because we need a dt on the bottom. So we need a dt, not a d anything else. The derivative of v with respect to t is called dv dt. The derivative of this, again, our derivative formulas don't change, so it's still 100 pi times the derivative L, but it's not dl dl this time, it's dl dt, which is not equal to 1. And that is, in fact, how fast the length is changing in time. And this is our answer for part B. This is the rate of change of the volume with respect to time is 100 pi times dl dt. So it's not a fixed constant, and this time dv dt changes. So depending on how the length changes, the volume will change according to this formula. If you want to write the units, again, the V is measured in cubic feet. So the top unit would be cubic feet. And the bottom unit is T, time. And we don't really have a variable for time yet. I should have written it up here. And I would have to look to the problem to see what they use in terms of time for seconds or minutes or years or whatever. Okay, so later on they say days. So in part C, they ask for how things are changing after 30 days. So I'll just do time in days. That way it'll line up with the rest of the problem. All right, so I didn't quite follow my own advice there by writing down the variables. I got a little shell shocked because I had written the wrong derivative in part A, but I fixed it. We're good now. We're good now. All right, let's do the last problem here, which is part C. I'll zoom up a little bit so you can read it along with me. For part C, it says if the length of the pipeline is being extended at the rate of 100 feet every day, how fast is the volume of the pipeline increasing after 30 days? So the question getting down to that is how fast is the volume of the pipeline changing after 30 days? So this is a change in volume, and that's in days. So we're looking for dv dt again, right? Not change in volume over L, change in volume over time. So we're looking for dv dt. But this time it tells us at a particular moment. The moment is 30 days. Right up here it says after 30 days. So we're looking for the change in volume over the change in time, how fast the volume is changing in time, specifically when the time is 30 days. We're also given some more information, so let's make sure we make note of that. Back up to the problem. It says the length of the pipeline is being extended at the rate of 100 feet every day. The length of the pipeline is being extended, getting bigger. So the length is growing at the rate of 100 feet per day. Feet is a measure of the length. Day is a measure of time. So it's the change in the length per the change in the days, the time. So that right there is going to be dl dt, the change in length over the change in time, right? So I'll write it here. Length is increasing. Was it 10? My short-term memory is so bad. 100. Increasing 100 feet per day. So again, we should write that in math language so we can use it in our formulas. So the length is the change in L, the time is the change in T, and that's going to be 100, positive 100, because it's increasing by 100. Okay, so we know that dLdt is equal to 100. You could even write down dLdt is equal to 100 down here. That's oftentimes done. We're doing the evaluation. We're evaluating it when t is equal to 30. We're also evaluating it when dLdt is equal to 100. All right, so now we have to find some formula for dV/dt and then put in the data, the information. We need to evaluate it when t equals 30 and when dL/dt is equal to 100. Well, fortunately, we found dV/dt in the previous problem, so I'll just write it down from right here. It's 100 pi times dL/dt. So now I'm going to put in t equals 30 and dL/dt is equal to 100. There's no t in our formula, so we don't need to plug that in anywhere, but we definitely need to find out, we need to plug in dL/dt. So this is dV/dt at the information that we are given. So I'll just say dV/dt at the info is equal to 100 pi times dL/dt, which is 100. And that is 10000 pi. And the units are V on the top, which is cubic feet. And the units on the bottom, T. T is measured in days. Oops, looks like I forgot to write day up here too. All right. All right, so that's our evaluation for how fast the volume is changing after 30 days, assuming that the length is changing at the rate of 100 feet per day. Okay, so let's do a little practice with the generalized chain rule with multiple variables and solving for things. And then we'll be ready for 3.9. All right, so I have some examples here. I don't have them lettered, so I'll just have to do them in order. The first one talks about this equation right here, y to the fourth equals x cubed plus a squared. And it asks us to find dy dx, and we're supposed to assume that a is a constant. So since we're looking for dy dx, there's got to be a dx in the bottom, and there's got to be a dy on top, of course. But in order to find dy, we just need any equation involving y, which fortunately is the one they give us right here. And to find dy dx, we need to just differentiate with respect to x. So we'll take our equation up here. I'll write it out here. And then we're just going to differentiate both sides with respect to x. That'll give us a dy dx. Okay, so this is how the chain rule works. We're going to differentiate everything using the chain rule. So the derivative of thing to the fourth is 4 times the thing cubed times the derivative of that thing. And on this side, we have the derivative of x cubed. So that's a thing being cubed. So that's 3 times x squared times the derivative of the thing. Now, a is a constant, and so we can't apply the power rule because the power rule does not apply to constants. It only applies to a variable raised to a constant. So this one is going to be plus 0 because the derivative of any constant is equal to 0. So why is there a ddx here? Because we did ddx in the beginning, because we want dy dx. So we just have to follow the instructions. We don't have to guess as to what variable we're writing in the top of the bottom. All right, so this is 4y cubed. Another way of writing ddx of y is just dy dx. The derivative with respect to x of y is called dy dx. This is 3x squared. Another way of writing dx is 1, because anything over itself is just 1. So now we know that 4y cubed dy dx is equal to 3x squared. All we have to do is just divide by this 4y cubed, and that will give us the value for dy dx. Okay. So that's how the chain rule works. You don't have to have it solved for y. You just have to differentiate both sides and use the chain rule. All right, second part of this problem is we're going to use the same variable, same equation, excuse me, and we're going to find dy dx, but we're going to assume that a is a variable this time. So instead of a being a constant, as in our previous example, we're going to assume a is a variable. What I'm trying to show you here is that things don't really change that much. So we're going to write down the same equation. We are looking for the same variable, the same derivative. We're looking for dy dx. So I need to differentiate with respect to x, just like before. And the difference is a is now a variable. It is no longer a constant. That's a variable. But our technique is going to be virtually the same. We just differentiate every time, writing the chain rule every time. So derivative of y to the fourth is 4y cubed times the derivative of that inside function, the y, which is just dy dx. We get the derivative of x cubed, which is 3x squared, times the derivative of that variable there, which is just dx dx, or 1. And then a is now a variable, so we have to differentiate this using the power rule as well. Derivative of a squared is 2a to the first times the derivative of that inside variable, which is the derivative of a, dA dx. And once again, we're going to divide by 4y cubed, so we can isolate the dy dx. Just y up here if my handwriting is not clear. And that will leave us just with dy dx. And then the right-hand side, I don't have to write dx dx, that's just 1, so I get 3x squared plus 2a dA dx over 4y cubed. And that is the value of dy dx, assuming that a is now a variable, so a constant. All right, we're going to do this another time. So the third part here is we don't have to do dy dx. We can do dy dt or dy d any variable. We don't have to choose any of the variables. We don't have to restrict ourselves to any of the variables that we have seen in the past. So in this third example, we're looking for dy dt. And again, we're going to assume that all the letters are variables. So we're going to start with some equation with y in it, which is exactly this equation right here, y to the fourth equals x cubed plus a squared. Because we're looking for dy dt, we want a t on the bottom, then we're going to differentiate this thing with respect to t. That will give us a dy dt. And then we're just going to apply the chain rule every single time, just as we've done in the past, and then solve for what we're looking for, which is dy dt. Again, I'm trying to show you how all these problems can be very, very similar, even though sort of they sound different. The mechanics, the actual calculus, it's pretty much the same every time. So derivative of y to the fourth, 4y cubed, times the derivative of the inside function here, which is dy dt. Derivative of x cubed is 3x squared times the derivative of the inside function, which is dx dt. And then we get derivative of a squared, which is 2a to the first, times the derivative of that variable, which is dA dt. They're all dt on the bottom because we're looking for dy dt. Now I just divide everything on both sides by my 4y cubed. And I simplify if possible. Before we had things like dx dx that like went away because they simplified to be 1. We don't have that right now, but it's okay. Answers can look more complicated. So on the top, we have 3x squared times dx dt. And we have 2a times dA dt. And on the bottom, we have 4y cubed. And that, my friends, is the derivative dy dt. All right. And we can do this with whatever letters we want, whatever order we want. It's just very flexible, the chain rule in this way. As long as we have the top variable somewhere, and as long as we differentiate with respect to the bottom variable, we can find any derivative for any of these equations. All right, so a couple more quick ones. I changed up the equation a little bit here. So now I have a squared equals b cubed minus c to the fourth, kind of similar, but moved around a little bit. And I'm looking for dA dx. If you haven't already paused the video, it might be a great time to pause it. See if you can find dA dx. See if you can find about dB dx. See if you got the idea of how this works. And then come back and I'll show you my solutions for these problems. So please give it a go if you're willing, if you have a little energy. And then when you're ready, come back and we'll check out the solution. All right, so welcome back. If you gave that a go, fantastic. I've written out my solution. Let's go over it with you briefly. We start up with this equation up here, the a squared equals b cubed minus c to the fourth. And for the first part, to find dA dx, I am just going to differentiate with respect to x on both sides because I need a dx on the bottom. The equation already has an a in it, so I'm going to get a dA dx just by differentiating it with respect to x. I use my normal derivative shortcut rules, and then I have to solve for dA dx, which means I need to divide by 2a at the end over here. So I divide this side by 2a, divide this whole side by 2a, and then I end up with the answer of dA dx is 3b squared times dB dx minus 4c cubed times dC dx, all divided by 2a. It's actually very similar to find the last here question, the dB dx. To find dB dx, we don't have to have a b equals equation. We just have to have b somewhere in the equation. So we already have b somewhere in the equation. It's right over here on the right-hand side. So I just wrote down the equation, and I took ddx of both sides. It's the same derivative, actually, because we're just differentiating with respect to x. So I get the exact same derivative. But now I need to solve for dB dx, which is not just a little bit of algebra. dB dx is over here attached to a 3b squared. And so all I have to do is do a little algebra and get it by itself. Hold on a second, I need to fix my pen. Okay, so all I have to do is add 4c cubed dC dx to both sides. That eliminates this part from the right-hand side, and I'll be left with this dB dx term with a 3b squared in front. And then I just divide by 3b squared to get rid of the 3b squared. And then I'm left with my answer for dB dx. It's this crazy expression right here, which looks a little messy, but you're used to that from math classes. Now, if we were given some information about what A, B, and C were, or what dA dx was, or dC dx, we could now plug that information in, which is what you'll be doing in the word problems. You'll be doing some crazy stuff like this, and then plugging stuff in to get a numerical answer at the end. I have one last example for you. It's a little bit less abstract, and it's where we're going to start off in the next video on 3.9. So I'm talking here about this example at the top here. A right triangle is expanding over time. X, Y, and Z are the sides, with Z being the longest side. We're looking for dz dt. So this is sort of a simplified word problem, but it has multiple variables. It has at least 3, X, Y, and Z. So let me draw a visual image here. Here's my triangle. It is a right triangle, so it has a right angle. We have side lengths of X, Y, and Z, with Z being the longest side. And we're looking for dz dt. Not sure what t is because it's not defined in the problem, but we can sort of think of dt as like the change in time. So we're sort of looking for dz dt. And in order to find dz dt, we need to have some equation with z in it, and then we need to differentiate that with respect to t. That's the game here. We need to figure out what we're given. We need to organize the information somehow. We need to figure out what the question is. Make sure you've mathed it up. Don't just write the sentence out in English. Write it out using our math symbols. And then we need some equation with the variable in it. We need to differentiate with respect to the correct variable, and then we get our answer. So with that, you may be thinking, what equation can we use? When we have right triangles, it's a good thing to think of the Pythagorean theorem. Also, similar triangles sometimes works, but this one is very nice with the Pythagorean theorem, which is a squared plus b squared equals c squared for all the right triangles. We don't have a, b's, and c's, but I'll write them in terms of the variables we have. X squared plus y squared equals z squared. So that's our Pythagorean theorem for these side lengths. And we're looking for dz dt. So that just means we need to differentiate everything with respect to t. We have a z in this equation. And if we differentiate with respect to t, we will get our dz dt. Now we just go ahead and do the chain rule. 2x dx dt plus 2y dy dt is equal to 2z dz dt. Oops, that doesn't look like a z to me. And what are we looking for? We're looking for dz dt. We're looking for this thing right here. And so I just need to solve for it, which means I need to divide everything by 2z. And that gives me dz dt equals, well, these divide out. So I'm just left with that big old mess. 2x dx dt plus 2y dy dt all divided by 2z. And that is our formula. That is our answer for what dz dt is for this triangle problem. All right, so hopefully that video was helpful in terms of remembering how this advanced chain rule works, as well as the idea of how to solve word problems with writing down the information in an organized way, writing down the question, using calculus, defining your variables, writing the variables instead of just writing English sentences, and then differentiating, getting the variables that you need. All right, please reach out if you have any questions or have any what if scenarios or need additional assistance. And hopefully I'll see you in the next video.